In all of our work with exponents and logarithms, we've come across exponential expressions, but now we're going to start setting them equal to each other so that we have exponential equations. If we're really lucky, we're going to end up with something that's got the same base on each side. Like this example here, 3 raised to the x plus 3. Sometimes that'll be in parentheses, sometimes it won't. You have to pay real close attention to the typesetting. Are they small and up there together? Are they intended to be an exponent? And then set equal to 3 to the 4th power. It should be fairly obvious, but because the bases are the same, I really can kind of just ignore them because I know what equality means, right? It means that whatever's happening over here has to be the same as is over here. And the only thing that's different on each side is the x plus 3 and the 4. So that's the only part I have to worry about while solving, which is super simple. X just equals 1. If I want to plug that back in to check, I'm looking at 3 raised to the 1 plus 3. Does that equal 3 to the 4th? Well, yeah, 1 plus 3 is 4, so we know we're good. Getting the same base is one of the most useful approaches. It's not always really obvious, and it's very rarely just handed to us. One example, 4x plus 2 is equal to 64. Well, off the first inspection, it doesn't look like they're related at all, but I'm looking at 64, and so my thought process at this point is 4 times 4, how many times will get me 64? Well, I know 4 times 4 is 16, and then 16 times 4, hey, there's my 64, so I know that I can just write 4 cubed, because it took 3 times multiplying 4 to equal 64. So we can rewrite that as 4 to the 3rd power equals 4 to the x plus 2, and we're right back where we were with our first example. X plus 2 equals 3, x in this case equals 1. Again, that's completely coincidental. The answer's not always 1. When we plug that back in and check, it's not quite as obvious. We've got to be real sure that we did this step correctly. 4 to the 1 plus 2, does that equal 64? 4 cubed equals 64, and we know we're good. Okay? Well, so far we've always had 1 equal to a number. What if both of our expressions have a little bit more going on than that? 81 raised to the 2 plus x is equal to 9 to the 10th. Well, we're always going to try to look at the greater value base and see if it can be rewritten as a power of the smaller one or the least one. In this case, 81 is 9 squared. But there was already an exponent there, so we're going to multiply power to a power. 2 plus x equals 9 to the 10th. We've got the same base, so we can just write 2 times 2 plus x is equal to 10. 4 plus 2x equals 10. Subtract 4. Divide by 2. And x equals 3. Still want to check it. So we're going to come up here. And I want to know, is 81 raised to the 2 plus 3 the same thing as 9 to the 10th power? That is not a number you want to try to figure out, even with a calculator. When we get ready to start, 9 to the 10th power times 9 times 9 times 9 times 9, that's going to get out of hand really fast. So let's clean it up and just use rules of exponents. 81 to the 5th power, is that the same as 9 to the 10th? And I already know that 81 is the same thing as 9 squared, and it's already being raised to the 5th power. 2 times 5 is the same thing as 10, so we're good to go. It's not always possible to make the same base on both sides. Take, for example, something like 8 to the x equals 16. there's not a convenient power of 8 that'll get 16. I watched some of you guys last week start fiddling with those decimal exponents. You'll get there eventually, but if we remember that logs and exponents are inverses of each other, I can undo this raising to the power of x by taking the log of both sides. Use my rule to bring the x out front, so it's x times the log of 8 is equal to the log of 16. Divide out the log of 8, and x is equal to. We just wrote log. We didn't write down a base, and we did that on purpose. We're using log base 10 because I want to be able to use my calculator. All right, when we can't make the bases equal on both sides, we're going to end up using the logarithm. We're going to pick up the calculator, and we're going to have to get a rounded decimal answer. So we'll just type log of 16 divided by log of 8. And for now, we're just going to kind of get in the habit of rounding to the nearest hundredth. So we're going to keep 2, check the third one. It's not enough to round up. So x is approximately equal to, remember the squiggly equal sign means approximately, 1.33. To check that, we're just going to plug it right back in the same way we did the other ones. Is 8 to the 1.33 approximately equal to 16? So pick up the calculator. 8 raised to the 1.33, and I get 15.889, which is pretty close. If it's not close enough for you, you can always add some more of those decimals in. And for every additional decimal value, we're going to get closer and closer to our value that we were looking for. Okay? So, same base makes things pretty simple. If you can't get the same base, there's always log, but we're going to be dealing with decimals at that point, so we usually want to save it as a last resort.